statement is estimate the thermal conductivity of polyatomic gas methane at 1232 Kelvin and 1.37 atmosphere using the Lennard-Jones parameter from the table. The molar heat capacity at constant pressure at 1232 Kelvin is given as 18.96 calorie per gram mole Kelvin, and we have to find what is the Prandtl number at the same temperature and pressure. So in this question we have given a polyatomic gas methane at certain temperature and pressure, and we have to use the Lennard-Jones parameter from the table and estimate the Prandtl number and the thermal conductivity of the polyatomic gas methane. So let's extract the data. The given temperature is 1232 Kelvin and pressure is 1.37 atmosphere, and we have to find out thermal conductivity and the Prandtl number. We know what is Prandtl number. Prandtl number is Cp into mu by K. Cp is the molar capacity and mu is the viscosity and K is the thermal conductivity. Now for methane we will extract parameters, Lennard-Jones potential parameters from the table. We will extract all the details from the Lennard-Jones potential parameter and critical properties table. So we will search which compound we are doing. In this problem we have CH4. So we will extract the data from this table. Molecular weight of CH4 is 16.04 and Lennard-Jones parameters. The sigma value is 3.78 and epsilon by K value is 154. And in this table we have also given critical properties like critical temperature, critical pressure and critical volume. The critical temperature for CH4 is 191.1. Critical pressure value is 45.8 atmosphere. Critical volume is 98.7 centimeter cube per gram mole. But in this question, we are only required molecular weight, sigma, and epsilon by K. So we will extract these values. Now we will use table E2 for determination of collision integral for viscosity and thermal conductivity. Since from previous table we obtained epsilon by K value is 154, and in the question it is given that temperature is 1232 Kelvin. So we calculated KT by epsilon is 8. Now we will search for 8 in this column, and we will get the collision integral value for viscosity and thermal conductivity. So corresponding to 8, the value of collision integral comes is 0.8538. We note down this and use in further calculations. So from the Lennard-Jones potential parameter table, we have estimated its molecular weight as 16, its sigma value is 3.78 angstrom, epsilon by K equal to 154, critical temperature 191.1 Kelvin, critical pressure is 45.8 atmosphere. So at the given temperature as per the question, we have to calculate at 1232 Kelvin. We will calculate KT by epsilon as we required in the formula. So KT by epsilon is 1232 divided by 154 is 8. So as from the table at KT upon epsilon equal to 8, we calculate from the table sigma mu or sigma K is equal to 0.8538. And now we will calculate the thermal conductivity as we have attained all the parameters that required in the formula. The formula is calculating viscosity is mu equal to 2.6693 into 10 to the power minus 5 into under root mt upon sigma square into sigma mu u. Now we will put all the values in the formula and we obtain the viscosity as 3.072 into 10 to the minus 4 gram per centimeter second. Now we will calculate the thermal conductivity. As in the question they have asked thermal conductivity value of methane as well. So the thermal conductivity is given as the expression Euchen approximation K equal to Cp plus 5 by 4 R into mu by m, where K is equal to the thermal conductivity, Cp equal to molar heat capacity at constant pressure, R equal to gas constant, ideal gas constant, mu is the viscosity, m is the molecular weight of methane. Now substituting the values in the formula, we will get thermal conductivity as 4.117 into 10 to the minus 4 calorie per centimeter second Kelvin. Oh, in the question they have asked us the Prandtl number. So the formula of Prandtl number is Cp mu by K. Then we will put all the values in the formula. Cp is 18.96, mu is 3.072 into 10 to the minus 4 as we just obtained. K we have get 4.177 into 10 to the minus 4, and we obtained the Prandtl number is 14.147, and the question is solved. We are having another question of estimation of thermal conductivity using the expression of Lorentz number. So what is Lorentz number? Application of kinetic theory to the electron gas in a metal gives the Lorentz number. The expression for Lorentz number is L equal to pi square upon 3 into KYE to the whole square. Basically Lorentz number is a constant, where K is the Boltzmann constant, E is the charge on the electron. And the problem statement is the electric resistivity 1 by Ke of copper at 20 degrees Celsius is given 1.72 into 10 to the minus 6 ohm centimeter. Estimate the thermal conductivity of copper in watt per meter Kelvin. So we have given the thermal resistivity and we have to use the Lorentz number equation to calculate the thermal conductivity. So now we will find out how we calculate. So as we know, for pure metals, the relationship between thermal conductivity K and electrical conductivity Ke are as follows: K upon KE into T is equal to the Lorentz number equal to constant. Basically Lorentz number is the constant values of thermal conductivity divided by electrical conductivity into the temperature. Here K is the thermal conductivity, Ke 1 upon K is the thermal resistivity, and T is the temperature at which we are required to find the thermal conductivity. It is also called as Wiedemann-French-Lorentzian equation. So in the step of solution, the first step is calculation of Lorentz number. We know the formula of Lorentz number is L equal to pi square by 3 into Kye to the power whole square, where K is the Boltzmann constant, its value is the universal constant, so its value is known. Its value is 1.3806 into 10 to the minus 23 joule per Kelvin. And we also know the charge on the electron, 1.6 into 10 to the power minus 19 coulomb. Substitute all values in the expression of Lorentz number. So L equal to pi square by 3 into 1.3806 into 10 to the power minus 23 upon 1.6 into 10 to the power minus 19, and we have calculated Lorentz number as 2.4494 into 10 to the power minus 8. Its unit is volt square per Kelvin square. Now our step 2 will be estimation of thermal conductivity. So we have the given of values of thermal resistivity, which is 1 upon Ke. The value is 1.72 into 10 to the power minus 6 ohm centimeter. So firstly we have to convert this into SI units. So in SI units it is 1.72 into 10 to the power minus 8 ohm meter. The temperature is given 20 degrees Celsius. We have also converted into Kelvin. So 20 plus 273 equal to 293 Kelvin. So we have all suitable units. Now we will put all the details into the formula. Is K upon K E into T equal to Lorentz number. So K is Lorentz number into Ke into T. Now we should remember that we have not given the value of Ke. We have given the value of 1 upon Ke. So while substituting we need to take care of that. Now we will substitute all the variables into this equation. Lorentz number 2.4494 into 10 to the power minus 8 into 1 upon 1.72 into 10 to the power minus 8 into 293. We have obtained the thermal conductivity value. K is 417.26 watt per meter Kelvin. Now we have estimated the thermal conductivity of the copper at 20 degrees Celsius is 417.26 watt per meter Kelvin, and the problem is solved.
Let's begin with our question. The estimation of thermal conductivity of a gas using Chapman-Enskog theory. Now the gas given here is argon, which is considered here in the question to be a monoatomic gas with molecular diameter given 3.4 angstrom, and the collision integral is approximated as 1.2. So now we will begin with writing the given details for the question and writing the Chapman-Enskog equation, and then we will put the numerical values and solve for the thermal conductivity estimation. Here the estimation of thermal conductivity of a monoatomic gas with given conditions. So we will initially begin with writing the given details for the question, where argon gas is assumed to be monoatomic gas. The given gas constant as 8.314 joule per mole Kelvin. The molecular diameter or sigma value, that is 3.4 angstrom. Here the collision integral needs to be calculated differently with provided details, but for the ease of question we have approximated it to the value of 1.2 at 300 Kelvin. Now the experimental value achieved for argon gas at 300 Kelvin is 0.0177 watt per meter Kelvin, and we will calculate here the K theoretical, that is theoretical conductivity, using the Chapman-Enskog equation. Here two types of equation can be given, and using the first equation we may calculate the results as follows. Now the values of molecular diameter is given and Boltzmann constant is given, and considering m is equals to molar mass upon the Avogadro number, we can calculate the thermal conductivity at the given details. So putting the values into the given equation, we obtain the theoretical value of thermal conductivity as 0.035 watt per meter Kelvin, which is in comparable range to the experimental value mentioned in the question. So the value might vary a little bit due to the consideration we are taking into assuming the constant collision integral and monoatomic gas behavior. So here we have calculated the theoretical value of thermal conductivity for the argon gas using Chapman-Enskog equation. Let us begin with this question. Compute the thermal conductivity of neon gas at 1 atmosphere in 373 Kelvin. For solution of this question, we need to obtain the Lennard-Jones parameters and critical properties from the E1 table that is given in the Appendix E of BSL book. Seeing the Appendix E given in the BSL book for referring to the collision integral values and the epsilon by kappa values, that is the Lennard-Jones parameters. So this is the table 1 that we will refer in the further video for different questions, where we can obtain the different required values like molecular weight, the molecular diameter, that is sigma given in angstroms, then epsilon by kappa value referring to the reference temperature, and then critical values, critical properties like critical temperature, critical pressure, critical volume, then here the critical viscosity and the critical thermal conductivity for different compounds such as neon, then uh, ethane. So here we can obtain the Lennard-Jones parameter. Now upon obtaining this, we will also need to require to refer the table E.2, which is for the calculation of Lennard-Jones parameters for different properties and like different temperature. So for whatever temperature it is required, we will multiply the kappa upon epsilon value into the temperature. Then whatever value we are getting, for example we are getting 1.2 value, then we will get the value for the collision integral, that is omega mu and omega k, as 1.455, and in case we can get the kappa epsilon into t value as 1.23, then we need to interpolate the value slightly for the collision integral, and hence we can get the collision integral value which we can further use in the question. These are the values for the molecular diameter. This is the value for epsilon upon kappa, and this is the molecular weight of neon that we have obtained from the E1 table of BSL book. Now as we have obtained the Lennard-Jones parameters from the E1 table of the BSL book, we'll move forward for the values required to put in the equation of the estimation of thermal conductivity. Now we'll assume the neon gas as monoatomic gas and further solve for the equation, that is kappa upon epsilon into temperature, which is obtained as 10.448. Now again we'll refer to the table given in the BSL book, table number E.2, for the value of the collision integral, which is from the table we can see that collision integral of mu, that is viscosity, will be equal to that of thermal conductivity, which is 0.821. Now using the Chapman-Enskog equation for monoatomic gas, which is given as K is equals to 1.9891 into 10 power minus 4 into under root of temperature upon molar mass whole upon molecular diameter squared into collision integral of thermal conductivity. Now putting these values in the above equation, as here we get the value obtained for thermal conductivity as 1.337 into 10 raised to power minus 4 calorie per centimeter second Kelvin. Now we have to make sure that the values we are putting in this equation are in CGS units, as converting to SI units will make the equation dimensionally unstable. Therefore, The thermal conductivity measured at the given condition of 1 atmosphere pressure and 373 Kelvin temperature for neon gas assumed to be monoatomic gas, the thermal conductivity obtained is 1.337 into 10 raised to power minus 4 calorie per centimeter second Kelvin.